finishing the chapter 2 on the paraplectic Brouwer algebra, just one more section. And then most of the talk today will be about what we can do with this for the paraplectic Lie superalgebra. So yesterday we saw that we could obtain the blocks of this paraplectic Brouwer algebra without actually computing many explicit decomposition multiplicities. We only had a very straightforward one, and then somehow that very easy relation generates the entire linkage. Even though the blocks are very big, they're somehow generated by a very simple relation. So when I put out the first preprint, I didn't really want to get into the computation of all the multiplicities because the paper was already getting quite long. But then later on, when I was discussing with Michael Erich about something we wanted to do after that, we realized we actually needed all the multiplicities. So together we actually computed them. So this is with Michael Erich. So to try and compute all these multiplicities, so they're these multiplicities of the simple modules in the cell modules. Basically, all tools that we need I've already presented. It's really a matter of using the restriction of cell modules, the action of the Juicy Murphy elements, and playing around with this in a way that you can basically more or less obtain the multiplicities for AR by knowledge for AR minus 1 and proceeding iteratively. So the algebraic aspect is not too complicated. I mean, once you have all those things that I presented yesterday. But to then actually take that iterative construction into something closed formula, a direct, explicit statement about the multiplicities takes a lot of heavy combinatorics. So I won't present the proof because it's really a lot of messy combinatorics. I think the paper is like 2 pages, some algebra, and then 12 pages working with what fell out of the algebraic manipulations. Although last week I heard that apparently John Brunden says that the only honest mathematics is combinatorics. And I'm in no position to argue with him, so at least for once in my life I was an honest mathematician. So that's also a good thing. So I'll present the statement. So these multiplicities are always either 0 or 1. And they're 1 if, as we've already seen, one partition must be included in the other. And furthermore, we need that the skew partition, so basically removing the smaller partition from the bigger one, you're left with the skew diagram or skew partition. This must be in some set of skew partitions. So I'll introduce that set in a second, of course, but already this statement is not completely trivial because apparently we have multiplicity 1, which is quite remarkable. For the ordinary Brouwer algebra, I don't think this is true. And what this also means is it's only this skew partition which is important. So already before we know what that set is, this basically means that, for instance, this multiplicity should be the same as this one. So the only thing which will be of interest is this big partition minus the smaller one. Sorry. That should make more sense. So already before introducing this set of skew partitions, there is some information there. Something else which is kind of implicit is that this doesn't depend on R being the parameter of the paraplectic Brauer algebra. So somehow the combinatorics of AR minus 2 is included in that of AR, which is kind of logical, seeing our construction with CR, which contained all of those algebras. So that's not very surprising. In fact, that is used in the proof. Okay, well, I'll try to introduce this set of skew partitions gamma. So I'll start by introducing some special cases, which I call the set gamma 0, which are a bunch of hooks. So I'll start by giving the smallest possible ones. So there are a bunch of hooks, including these ones. So what is important is that the width, so the number of rows that the hook is spread over, is one higher than the height. So that's the case for any of these. So that's one condition. And the second condition is what we call the diagonal condition, which says that if I start by drawing a diagonal here in the first box, that I'm never allowed to go above that. So I can be on the diagonal but never above it. So, for instance, this partition, even though the first condition is satisfied, is not in there. So they're basically some kind of Duke paths, where I have to basically reach some endpoint, and I can do it in whatever way I want, but I can never be above the diagonal. So they're very closely related to that. So these are some special cases of this set. So they're all skew-Young diagrams in their own right. And gamma is then basically defined as the set of skew-Young diagrams that I can build out of these ones. Built in a way that they are the union of some nested elements. In gamma 0. So by this I mean that for example, this is an element in gamma because I can break it up into this element of gamma 0 and this element of gamma 0, where if they happen to touch, the entire down right side of one is touching the other. So it's kind of nested in that way. So another example would be this. No, sorry. Need to add that one, of course. So I have two elements of gamma 0 nested like that. So it's always that principle. So I think the best way to show how this works is usually, I think in practical examples, you wouldn't really think about the set gamma, but rather proceed as follows. So let's do a full example. You would have one partition lambda like this, and some bigger partition mu. about as big as should be allowed to draw on a board. So if you would be given two partitions, lambda and mu, and the question is, what is this multiplicity? Is it 1 or 0? The way to proceed is to first, of course, single out the smaller partition in the bigger one. And then we just remove one by one as big a rim hook as possible, which doesn't intersect with the smaller partition. So we start by just removing this entire rim hook. And we check whether it is in gamma 0 or not. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So that condition is satisfied. Also the diagonal condition is clearly satisfied. So we just throw that away, look at what is left. So now we imagine that the red line is no longer there. I think if I would have to draw it over, it would take a long time. And we just do the same thing. We remove the maximal rim hook. So again, it is in gamma 0. You've got length or width 1, 2, 3, 4, 5, and height 1, 2, 3, 4. And you never go above the diagonal. You go on the diagonal, but never above. So we've gotten this far. And now we again remove the maximal rim hook, which doesn't intersect with the smaller partition, which now becomes a relevant condition. And then, of course, it's disconnected. I get these two things, which don't touch, so they don't have to be nested or anything. And they're also both in gamma 0. So we find that this is actually 1. So that's just the algorithm. You just remove as big a rim hook as possible, one by one, and each time you check whether that rim hook is in here. Okay, so that's the explicit description of the multiplicities of the simple modules and the cell modules. So then we come to the third chapter I'm going to talk about, which is now the representation theory. Yeah, it's only 1 and 0.
So why can it never be greater than 1?
It's
easy to see.
it's not very easy to see, no. I mean, it wasn't particularly easy to prove, even. We kind of first, we had to prove that only these multiplicities exist, and then we could go back in the proof and prove that it could only be 1. It wasn't even a direct proof. It was somehow a bit messy. Or maybe there was one, but we didn't see it, so we did it. Yeah. I can't claim I really understand this. I just proved it, which is a weaker statement. Yeah.
It's whether it's easy to see in the negative. I don't know. I cannot see.
Yeah, it's easy to see for the specific one that I needed for the blocks, but in general, I don't know. Well, it should be connected to the corresponding results for the representation theory of the perplexity superalgebra, but I can't explain that that feature either.
I have also this projected with multiplicity 1.
Yes.
It's also not easy to see.
Yeah. So we'll see that it's
two algorithms.
Yeah, of the algorithm. From that you can see.
So we introduced the algebra AR as some algebra of endomorphisms of the tensor power of the natural module for this algebra, and now we get back to that algebra to see what we can do with our gained knowledge. So let's first talk a little bit about the structure of this Lie superalgebra. So as already mentioned on the first day, we can realize it in terms of matrices as follows. So A is arbitrary, B is symmetric, and C is skew-symmetric. And the multiplication is given by the supercommutator of these matrices. So the even part were the two diagonal blocks, and the odd part were the two off-diagonal blocks. So in particular, we see that the underlying even Lie algebra is given by GLN. And also that G has some three-term Z grading.
C transpose B minus C.
Sorry?
C transpose minus
Ah, yes. Thanks. Otherwise, life would be a lot easier.
Yeah.
We wouldn't be having this mini course probably. Yes. So this is some Z grading, where the G1 part is just given by B and the G minus part given by C. There's some clear Z grading. So the odd part is built out of G1 and G minus 1. And in particular, we see that as a modulo over G0, G plus 1 corresponds to the symmetric power of Cn, and G minus 1 is the skew-symmetric power of the dual of Cn. So we have a triangular decomposition. We could make several choices, but I'll just choose one as follows. So here in the A part, I take this to be plus and this minus. Then I take the minus the transpose of A, so of course here it's reversed. And I take this entire block to be in n plus, and this block in n minus. So, in particular, the Borel subalgebra is given by the Borel subalgebra, the standard Borel subalgebra of GLN plus G plus 1. And H is of course just a Cartan subalgebra of GLN. So we take a basis epsilon 1 up to epsilon n of the dual of H. So the usual basis, by which I mean the positive roots for GLM, so the even positive roots in this basis are expressed as epsilon I minus epsilon j for I smaller than j. And that's of course equal to minus the negative roots. So based on this description of g plus 1 and g minus 1, we can immediately find the odd roots. So they're given by the weight of those representations. So we find that the odd roots, the odd positive roots are given by epsilon I plus epsilon j. And the negative roots are given by minus I minus epsilon j. But here we're in this Q symmetric power, so I has to be strictly lower than j. So of course the difficult thing about the paraplectic case is that we don't have that the positive roots are minus the negative roots. So this is the only Lie superalgebra in our list which has this remarkable property. And more or less as a consequence of that, we have also a weird behavior of the center. So the center of the universal developing algebra. So for all these superalgebras in that list, the center is somehow, or for almost all of them, the center is a lot less powerful than in the Lie algebra case. But in this case, it's really extreme. For instance, if you think about the most common element of the center of reductive Lie algebras in developing algebra, quadratic Casimir, one of the ways to express it is to say you've got some stuff in the Cartan, and then you pair up the negative and the positive roots in some way. But of course here that doesn't make sense. So there's no Casimir, and it turns out that there is basically no center. So this was proved in 2001 already by Maria Gorilik. So the center acts in the same way on any simple module. So I'll just phrase it as the center is contained in the Jacobson radical. So the Jacobson radical is everything in universal developing algebra which annihilates any simple module. So this is not quite true, of course. It would be more correct to say that the image of this in the quotient with respect to the Jacobson radical is just constants. Okay, let's just say it's basically contained in there. And already the fact that there exists a Jacobson radical is remarkable. Because for Lie algebras it doesn't exist, and for this is also the only Lie superalgebra in that list for which there is a non-trivial Jacobson radical. It's not very difficult to see that there must be such a radical, because if I would apply all positive roots, so that product of all positive roots, that must be in the Jacobson radical. Because if I apply that to a simple module, I don't have enough negative roots to go back to where I started from. So I end up in some submodule, and it's a simple module, so must have killed it. So it's rather immediate observation, but it's a unique property. And in fact, fortunately I don't have time to go into detail about this, but there is some nice paper by Vera Sorganova who studies the representation theory of the quotient of the universal developing algebra by that Jacobson article. So somehow things get a bit nicer then, and you can do a bit more, at least certainly at the time, and get some nice results. So not just for finite dimensional modules like we'll do, but for arbitrary modules. But I'll just mention it. Because the only thing that I will speak about here are finite dimensional modules. Because for Lie superalgebras, contrary to simple Lie algebras, their finite dimensional representation theory is quite interesting. I mean, even without looking at the tensor structure or something, just the character formulas and the blocks and everything. So I'll talk about the category F, and when I want to specify which paraplectic Lie superalgebra, I'll write Fn. So everything here can be found in a paper by G from 2015. So this category is a category of all finite dimensional integrable Z2 graded modules over this paraplectic Lie superalgebra. And we consider all morphisms, so not just parity preserving. So integrable more or less means weight modules, slightly stronger condition, but basically means finite dimensional weight modules. So they need to be Z2 graded, so they're Z2 graded vector spaces such that the action of this is compatible. An odd element interchanges even and odd subspaces, etc. So it turns out that this is a very nice category. It's abelian. It's locally finite. So objects have finite length. Well, that's logical because they're finite dimensional. Morphism spaces are finite dimensional. There are enough projectives and injectives. So basically, locally, this looks like a category of finite dimensional modules over a finite dimensional algebra. But it just happens to go on infinitely long, but locally it's a very well-behaved category. And the simple objects are the simple highest weight modules. With their highest weight in the set of integral dominant weights. So that's this set, I'll call it X plus. So I didn't want to use lambda, mu, etc. because I already use them for partitions. And then I decided to use omega, which is a bit dubious because that's usually for fundamental weights. But so their weights, which are descending, and all elements of the integers. So for omega, I interpret it as omega 1 plus times epsilon 1, etc. So I'll write S omega for the simple module. So usually I would write L, but also to make a little bit of a distinction with the paraplectic Brown algebra. So for instance, S of 0 is nothing but the trivial module, and S of epsilon 1 in this convention is the natural module, which is self-dual. So, contrary to the simple Lie algebra case, this category is certainly not semi-simple. It behaves a bit like a parabolic version of category O, in some sense. So, for instance, we have an analog of parabolic Verma modules, which are known as Katz modules. So they're defined like this. I start from a simple GLN module. So I write S0 of omega. So this is a G0 module. I interpret it as a G0 plus G1 module by letting G1 act trivially. So, and then I induce from this subalgebra to the entire algebra. So this is really an analog of a parabolic Verma module. This is the parabolic subalgebra. So, contrary to parabolic Verma modules, this is actually finite dimensional as this module. The reason being that the universal developing algebra of G minus 1 is finite dimensional. So that's why this is somehow in the category of finite dimensional modules. But here our choice of Borel subalgebra is not canonical. We could have used the G minus 1 part to create a Borel subalgebra or a parabolic subalgebra, and that would give something strictly different because it would even has a different dimension. So it's certainly not linked by an automorphism. So this is somehow one choice for Katz modules, where the other ones aren't just linked by some automorphism, autoequivalence of the category or something. So these are known as the thin Katz modules. So they're thin because as a vector space they correspond to the product of the exterior algebra of G minus 1 and this one, and G minus 1 is the smaller of the two, G minus 1 and G plus 1 that we have. So this is somehow the smallest module of the two, the smaller of the two. And the other one, for instance, E of W, we could define by inducing, starting from this parabolic, but do the same procedure. So it's again finite dimensional, but now the dimension corresponds to the exterior power of G1, which is bigger, so this is the thick cuts module. So something that we can observe immediately is that the thick cuts module can never be simple. It's too big to be simple. So if we start with this subspace, we've acted with everything in G1 to stay inside this module, and as I said before, we can't go back, so this one can never be simple. This one can be simple. It generally won't be, but it can. In fact, it's possible to be a bit more specific. And this is the following. There are some multiplicities, and this was proved by Chibi, which we know must appear. For instance, this one can't be 0. I left a bit of room here because there is some shift which appears, but I want to ignore it because it will appear a couple of times. So in principle, I need to add something, say gamma, which is a GLN weight which is constant. So it wouldn't be seen by SLN, but it is seen for GLN. So it's kind of some shift. But I think it wouldn't really give extra value within the bounds of this talk to keep track of it all the time. So this is a minor lie. So I think that this is somehow very similar to the one decomposition multiplicity that I already showed you yesterday, which I said this one is rather easy, because it's really the same philosophy which appears. We create some potential submodules which we know cannot be killed, because we have no symmetry between n plus and n minus, which is exactly the same thing that I used to prove a very similar looking decomposition multiplicity, which must exist again by lack of symmetry. So this is somehow very closely related. So this is very close. To this thing. So somehow the lack of symmetry can sometimes help to gain some decomposition multiplicities. Okay. Then another result by Chibi is that there's also some BGG reciprocity. Again, there is some kind of twist in the sense that so projectives will have filtrations by both types of CUTS modules, and the multiplicities of the filtrations satisfy this relation. So the number of times the thin CUTS module appears in the projective is somehow similar or the same to the number of times a certain simple appears in a thick CUTS module. So it's somehow logical that these are interchanged. The smaller this module is, the bigger the multiplicity, the bigger that module must be. And logical. And also the reversed implication is true. So again, the BGG reciprocity results are somehow twisted, but in a different way than we had yesterday. But still, this means that if you understand the standard modules, so the CUTS modules, both of them, then we understand linkage, because then we know what the project is, or at least what the characters of the project is, or the composition multiplicities, or the Cartan matrix. So, some results about linkage in this category. So there is an equivalence relation on this labeling set X plus, which is generated by two relations. First is that omega is equivalent to omega plus 2 epsilon I for an arbitrary I. And the second one is that omega is equivalent to omega plus epsilon I plus 1, again for an arbitrary I. But here only under the condition that omega I and omega I plus 1 were the same. So if two subsequent labels are the same in omega, I'm allowed to change them. And I'm always allowed to add 2 to any label. Of course, the unspoken condition is that these things must be in X plus. So that's a non-trivial condition, but so it's linkage on X plus if both sides are in X plus. If both sides make sense, then they are linked. And then we have the following theorem. If we have a relation in this equivalence relation, then the corresponding simples are in the same block. So we've already seen part of the proof. This relation here is covered by this statement. I should of course mention that this one has a simple top or simple socle corresponding to that omega up to shift. So that one is governed by computing some multiplicities for the thin CUTS modules. You can prove that this one must provide linkage. So this is a very remarkable result because it implies that we have at most n plus 1 blocks. And so, as I said, this is quite remarkable because this is the only Lie superalgebra in the list that we've seen that has a finite number of blocks. It's yes, yeah. Well, yeah. I mean, yeah. You could take a one-dimensional something, right? Yeah, so this is somehow very weird, that you have finitely many, and it's also not 1 or something, it's just n plus 1. It's really, I think, pushing the boundaries of acceptable behavior. But this is just what happens to be the case. So we have all this linkage, which is quite strong. So I say there are at most n+1 blocks. That's because any weight can be shown to be linked to one of the following. So I have n+1 integral dominant weights here, and the claim is that any weight can be linked to one of those using these two relations. So therefore at most n+1 blocks. So the question which remains open is there some linkage in the blocks between the modules with these highest weights? So the question is, how can we disprove any linkage? So for the other cases, say GLMN or OSPM to N, one computes linkage in this way. You take the CATS modules or some finite dimensional modules, you can obtain some linkage from that, and then you use the center to disprove any further linkage. But here we have no center to help us out. So, but there are some things that you can observe anyway. For instance, if I sum over all the coefficients of my weight, and I take this modulo 2, so I just look whether it's even or odd, then that is preserved under linkage. So I do have some kind of even and odd blocks. So that's just because all the roots preserve this. So I only had epsilon minus epsilon or epsilon plus epsilon or minus epsilon minus epsilon. So I can never mess up this invariant of a weight by acting with the roots. So one thing which is more difficult to prove but still true is that this one is actually a block. So it's possible to prove that this one is not linked to anything else. By brute force, by observing that the thin CATS module is always simple here for anything which is linked to that way. So I think that was already proved by Serganova. And I think Chibi computed the decomposition multiplicities for the thick ones. So they're not simple, of course, but I think for the ones linked to that weight, he had a full formula.
The only one that's actually where the CATS module is simple.
Yeah. Well, yes, but there are still typical ones here, but this is the only block which is entirely typical. So it's very weird. So this is not like the typical block, because there are also typical stuff elsewhere, but this is the only purely typical block. Yeah. So this open problem is what originally made me think about everything that I've presented so far. So I saw this nice result with only finitely many blocks and the open question, how can we disprove linkage? And I thought maybe the paraplectic Brauer algebra can somehow help us out. If I can obtain the blocks for that algebra, maybe I can use that to obtain them for the paraplectically superalgebra. And I thought the blocks for the paraplectic Brauer algebra should somehow be more manageable because that's a finite dimensional algebra. There has to be something which separates the blocks. There has to be some central element in the algebra which separates things. Of course, it could be difficult to find, but at least there has to be something. So as we've seen yesterday, it's possible to obtain the blocks for the paraplectic Brauer algebra. So now I'll show how one can use that result to come to a full conclusion on the blocks of the paraplectically superalgebra. So the reason that we might hope to get some results on the blocks of Fn using the paraplectic Brauer algebra, because originally it's just some algebra for the invariant theory, but there's a good reason why it's really helpful in representation theory in general.